Hey guys, Mr. Palmer here with another chem video. This time we're going to be talking about spectrophotometry. Spectrophotometry is a technique that you're going to use in general chem and AP chemistry, and it allows us to do two things. Really, what you're going to be doing is measuring the absorption of light of various wavelengths by a solution, some sample. And that could do two things. You can either use it to identify a substance by looking at the particular pattern of absorption that's created, or you could, and this is what we use it most often to do, calculate the concentration of an unknown solution by comparing it to the absorption of some standard solutions of known concentration. So this slide, you're seeing a diagram of what a typical spectrophotometer looks like and the components, but I'm going to start by going through sort of a simplified diagram to show you what the inside is like of a spectrophotometer. So what are we doing in a spectrophotometer? We're going to be looking at passing light through a sample. We want to look at what's absorbed, so we need to start with a light source. So in my diagram here, you see a light source on the far left. It's an incandescent bulb. It could be an LED light as well, but it's some sort of light source. It's going to put out photons for us. Importantly, there's a wavelength selector. So in wavelength selection, the next thing that happens is the light, the white light's going to get split up by what's showing you here is a prism, but more likely to be a diffraction grating that's going to spread the light out. And the other part of that is the actual selection mechanism, which is a slit or some kind of control that allows us to only let a narrow band of wavelengths through into our sample. So that light, in this case showing some blue light, passing into a sample. The sample compartment, we're using a piece of glassware called a cuvette, which is just a special test tube holding our sample. It has a fixed length, the length of that sample, or the width rather, we call B. And then you're going to see some transmitted light coming out the other side, a little bit less light because some was absorbed, and going into a detector, a photoresistor, photodiode. And then the output of that is going to be sent to a meter, and that allows us to read off either percent transmittance or absorption. And that's what you're going to read off from a spectrophotometer. So what are these two things? Well, the simplest to understand is transmittance. So what is it? Usually we're reading percent transmittance. This is just the ratio of light transmitted through a solution to the light directed at the solution. So that's the ratio right here. So if we go back to this diagram, the light that's being directed through it, I-O, compared to the light that comes out, I-T, that ratio right here is our transmittance. So if we call this percent transmittance, 50% transmittance would mean that half the light that went in is actually going to be transmitted out. That means half of it's going to be absorbed. We're more likely to use absorbance as a measurement, and we'll talk about why that is a little bit later. But absorbance is what we're going to use, and absorbance is a measure of the light absorbed by the solution. So it's sort of the inverse of what your transmittance is, and it's calculated as the negative log of your transmittance. So obviously as the percent transmittance goes up, or the amount of transmitted light increases, the amount that's absorbed must be going down, and vice versa. So we're gonna look at absorbance. So let's go back to an actual spectrophotometer and how this actually operates. So you're going to see that we have a sample compartment first. So the sample compartment, you see an enlarged diagram of what it looks like with the lid open. When the lid opens up, that's where you can put your cuvette in, that special piece of glassware. Some are round, some are square. What's important is that they're the same. That is, if we're putting in different samples, we want to make sure that it's the same glass, it absorbs the same amount of light, it's the same width, so we have the same path length, and that doesn't change. The light's going to go through it. What kind of light? Well, we have a wavelength selector wheel. You see that over on the right of this one, and there's some kind of device that allows you to choose your wavelength. When you set the wavelength, most of them have a filter on them. So if you look on the far left of our diagram of the picture, you see this filter wheel, and there's a zoom in of the tag that's on it. you'll see that the filter wheel, in this case, it's set at blue. You'll see a little blue right there on the wheel. And blue is used when you have 375 to 540 nanometers. If you're going to change the wavelength, you need to adjust that filter to coincide with the wavelength that you're going to use. And then there's a display that's going to read out what you want. And there's these two knobs in front. There's a 0 knob and a max absorbance knob. Most of them have 2 knobs. Some only have 1. But what we do use these for is to zero the machine. First of all, we're going to set it to be 0% transmittance, right? Blanked out. And then we're going to put a blank sample in, one that contains just water. This is our blank. And we're going to set that with the other one, which is our max absorbance knob. We're going to turn that to 100% T. Now, I'll show you that in just a second. Most of them have an instructions on it, just like this one. So this one has operating instructions. It tells you to turn it on and let it warm up for 20 minutes. That's going to let the light bulb, I think, come up to temperature and have sort of like a consistent amount of light coming out. So it's stays the same throughout the trials that you're going to be doing. You first set the wavelength. That's the first thing you're going to do. And then you're going to adjust the 0% T. So that's when it's telling you the 1 knob here in step 3. You want to adjust it using the 1 knob so that we're reading 0% T. And then we're going to insert the blank. And I said the blank is just a cuvette that has water in it, or whatever the solution is that we're going to be diluting our substance that we want to be measuring the absorbance of in. Usually it's just distilled water that we put in there. And we blank it. That is, we put the blank in and we adjust it to 100% transmittance. And that's usually on a different wheel or a different dial. And we set that to say, okay, here's our distilled water or deionized water, and this is 100% T. That is, we're going to say this has 0 absorbance. You then put your sample in, right? And we're going to compare the sample to the blank. So if the blank is 100% transmittance or 0 absorbance, we put in our sample and we read what the absorbance of that sample is. And then you set the mode and you can take the reading off of the readout on the device. I did put here, typically we're setting a peak wavelength. We want to measure wavelength for a substance at the wavelength that measures or that absorbs the most amount of light. Or, you know, sometimes if we were going to just look at what the substance is, we might sweep across all the wavelengths. But every time you adjust the wavelength, you're going to need to re-zero your device, and you're also going to re-blank your device. So if you change the wavelength here, you're going to go back to step 2, setting the wavelength. You need to readjust your %T and readjust to 100% T, that is, re-blank it. If you don't have a spectrophotometer, there's a much simpler version of this that you can use. It doesn't take quite as much effort. However, this only allows you to pick specific wavelengths, and this is called a colorimeter. Here's a very simple colorimeter. Obviously, you don't see any display on here. You would have to attach this to maybe a data collection device like a LabQuest or LabPro. And it has the same components. It has a sample container where you're going to put a cuvette. This one happens to be square. You can blank it just exactly the same as you did the other one. But you'll see this knob, the wavelength selection, you only get 3. So rather than using an incandescent light, they just use 3 different LED lights inside that have a very specific set of wavelengths. And usually they give you a range. We've got green, red, and blue. So you can pick the wavelength that best or most closely fits the peak absorbance of your material that you're going to use. So this will only allow you for this one to look at 635, 565, and 470 nanometers, a red, a green, and a blue. So let's talk a little bit about the electromagnetic spectrum. Obviously, we know that light comes in various wavelengths. In this kind of spectroscopy, we're really looking at UV vis, that is ultraviolet and visible light. So the spectrophotometers that you would use in a lab are going to be probably somewhere between 300 and 800 nanometers, depending upon the, what the brand of it is. There is a different type of spectroscopy in the infrared range, but that is a different kind of device. So we're focusing on ultraviolet and visible light, and most of the materials that we're going to use are things that absorb in this spectrum. So if you're going to use visible or UV vis, you have to use something that is absorbing in the ultraviolet and visible range. So you would want to use ions like copper ions or nickel ions. You would look at them because they have a distinctive color. Maybe iron ions. Maybe we're looking at food dyes, or maybe indicators like crystal violet. We'll look at one lab where they actually have strong absorbance in this range that allows us to analyze them. So you wouldn't want to use something, or you couldn't use this to look at something like sodium or potassium ions that don't absorb strongly in that range. So if they're not going to absorb light, then it's really not possible to use spectroscopy to measure their concentration. Here's a sample graph. So let's say you were going to sweep across the wavelengths and look at something like chlorophyll, and we were to plot it out. So you're going to see that chlorophyll gives you a graph, this white line coming across from the violet all the way to the red. There's this kind of strong peak absorbance here in the violet range, and there's a strong absorbance somewhere in the red range, and very little absorbance here in the middle range in the green section. And that is in fact why chlorophyll is green, because it's absorbing ultraviolet light, it's absorbing red light, and it's transmitting the green light. That is, it's not absorbing it, and that's why it's going to appear to be green to us. So this could allow you to identify a particular material. If we're looking at something like food dyes, here's some student data. I had some students collect data on various food dyes: blue, red, orange, yellow, and green. And you'll see, well, what does blue food coloring look like? If you look at the blue, it's got a nice absorbance here in the red range. Very little absorbance up here in the blue and violet range. Yellow light absorbs in the violet range, and then very little in the green and red range, which is why it's going to appear to be blue. If we're mixing those two together to make a green food coloring, which is how they make the green food coloring, we're going to see that the green line has absorbance just like the yellow in the violet section, and it also has absorbance in the red section, just like the blue. And that's what's going to make it be green. There's very little absorbance here in the green section. If you look at something like red, well, here's the red food coloring. It's got a peak absorbance somewhere in the green section. It absorbs some in the blue as well, but very little in the red part of the spectrum, and that's why that's going to look red. So if we were trying to measure the concentration of red food dye, well, where would we want to go? We'd want to go and use the place where there was a max absorbance, somewhere a wavelength between 500 and 550. Now, if we're using this to find the concentration of a solution, we're using really what's called the Beer-Lambert Law. And as I mentioned earlier, we tend to use absorbance for most labs when we're looking at things, because the absorbance of light, right, unlike using the transmittance, is directly proportional to the concentration. So that's really helpful. That allows us to create a nice best fit line. It's a linear relationship and allows us to really take something of unknown concentration and calculate its absorbance using this. And I'm going to show you how to do that in just a second. The other two parts of this equation, the Beer-Lambert Law, are the path length. So how much solution does the light travel through? And the molar absorptivity, that is, how much light is absorbed for that substance at a particular wavelength. So it depends on what the substance is and what wavelength we're looking at. So for a spectrophotometer, we really keep these two things constant. If we use a cuvette that has a fixed path length and we have the same substance, right, we keep these two fixed. We can simply look at absorbance and concentration and see how they vary. And what we're going to do from that is create what's called a Beer's Law plot, or calibration curve. So this calibration curve, we take solutions of known concentration. So let's say I take a 0.5 molar solution and I dilute it to 0.4 molar, 0.3 molar, 0.2 molar, 0.1 molar, and then I measure the absorbance at each one of these concentrations. So I know the concentration very, very accurately. I measure it carefully. I put it into my device at the max wavelength. I pick a wavelength that has a strong absorption for my material, and I plot it on my graph. I get a nice best fit line, and it's a linear relationship. Now you'll notice I did put 1 on here. We don't want to really, we want to pick concentrations that have a absorption that doesn't really go above 1, because what's going to happen is this is no longer linear. Once you get up above 1, this graph starts to kind of level off up there. So we want to keep it below 1 for the absorbance. So you're going to adjust and pick concentrations that are appropriate for your material. It's going to depend on your spectrophotometer, what the substance is that you happen to be looking at. And obviously we can find an unknown material. If we measure its absorbance, we could plot it on our graph, find the concentration, and obviously we don't need a graph, put it on the graph. We can just use our equation for our best fit line and calculate what that concentration is going to be. So let's look at some sample questions about this. So what I'm giving you is a nice graph here of a couple different substances. I'll just read through the prompt. This graph is going to show the absorption of light of various wavelengths recorded by a spectrophotometer. The different lines represent solutions of 0.1 molar copper 2 ion, 0.1 molar nickel ion, and a solution that's made by dissolving a nickel coin in acid. And a nickel coin contains both copper and nickel metal as part of that coin. So it's going to be somewhere in between the absorbance of the two. So let's look at our question. Which of the following would be the best choice of wavelength for a spectrophotometer to create a Beer's Law calculation curve for nickel 2 ion? So take a second. Okay, let's go through it. You're given the choices of 400 nanometers. Well, we're looking at nickel. Nickel's our blue line. 400 nanometers, it's got an absorption up here around 0.7. 500 nanometers, it's close to 0. 650, it's around 0.3. And at 800, it's somewhere a little less than 0.2. So what would be our best choice? Well, we would want to pick the one that has the highest amount of absorption. So we're going to pick the one that's at 400 nanometers. Now, keep in mind, it's not the one that has the highest wavelength. It's the one that has the highest absorption. Let's look at the question a little bit differently. So, different question about this one. Let's look at the copper instead. Which wavelength setting on a colorimeter would be the best choice for creating a Beer's Law calibration curve for copper 2 ion? Now, copper 2 is the red one, so make your selection. Hopefully you said 635 nanometers. If we take a look at our graph, 350 nanometers, well, there's really nothing being measured down there for copper. 470, 565, still very little. 635, now we're up here around 0.2, so that's why this is our best choice. A, B, C, D. Let me fix that. It should be choice D. Now let's look at a slightly more realistic problem, a lab-based question. So let me work you through the prompt here. A student constructs a Beer's Law calibration curve for copper 2 ions, along with a best fit line, the equation given to you. If you can't read it on here, it's given to you in the prompt. The student then dissolves a 0.805 gram piece of brass, which contains copper and zinc, so it's in brass, in 15 milliliters of 6 molar nitric acid, and then diluted it to 50 milliliters with distilled water. The absorbance of the brass solution was measured at the same wavelength that was used for the copper 2 standard solutions. The absorbance of the brass solution was found to be 0.401. So let's look at our two questions down here. First, you're asked to determine the number of moles of copper in the brass sample, and second, to determine the mass percent of copper in the brass sample. So if you want to pause the video, take a few minutes to calculate these, and then I'll go through the answers. Okay, so let's look at the first one. Determining the number of moles of copper in the 0.805 gram brass sample. Well, we're trying to find the moles. We would need to know the concentration, and that's where we're going to use this calibration curve. We're going to go back to our curve. We know that it has an absorbance of 0.401, somewhere in here. So we're going to find out what that concentration is. Now, obviously, we're not going to do it from the graph. We're going to use the actual line of best fit. So let's go back to the question. Our line of best fit is y equals 3.3253x minus 0.0229. Now, remember that x is the concentration, and y is the absorbance. So we can substitute in our absorbance. We know the absorbance is 0.401 in for our y. Switch colors. 0.401 equals 3.3253x minus 0.0229. And that's going to give you an x value, that is a concentration for this, of 0.127 molar. Now that's not the final answer, that's just the concentration. We want to know what the moles are. So if we're going to determine the moles, we're going to use molarity times volume. Our molarity of 0.127. And our volume, what volume are you going to use here? Let's go back to the prompt. It told us that we dissolved this with 15 milliliters of nitric acid. Now that's a little bit tricky. It's a little bit tricky because we're not going to use the 15 or the 6 here. What we're really interested in is the volume of the solution. Remember, it was diluted with water to 50 milliliters, so that's the volume that we're going to use. We're going to use 50 milliliters in liters, 0.0500 liters. Liters times molarity is going to give us moles. So if we multiply those together, we get 0.00637 moles of copper. Okay, little tip on the sig figs. You'll notice in the prompt we were only given 3 sig figs here for the absorbance. So when I put that into our best fit line, we're left with 3 sig figs for concentration. We have 3 for the volume, which leaves us with 3 for our final answer. So you'd want to report that with 3 significant figures, 0.00637. So let's look at part B. So part B asks us to find the mass percent. And remember, mass percent is the mass of the thing that you're looking for over the mass of the total. So what's the total? The total was the piece of brass, which was the mixture of copper and zinc. So it's 0.805 grams. We need to find the grams of copper. Well, that's pretty easy. You've already found the moles, 0.00637. So if we know that we have 0.00637 moles of copper, we can turn that into grams. We're going to go to the periodic table. We're going to look up the molar mass, 63.55 grams of copper in every 1 mole. That's going to be 0.405 grams of copper in the sample. Again, that's not the mass percent. We need to put that over the total. What was the total? 0.805 grams of brass. To make it a percent, we're going to multiply by 100, and that gives us 50.3%. And again, I'm reporting to 3 sig figs because I had 3 sig figs here. I was given 3 sig figs in the prompts for the brass mass. So that's my percent of copper in my brass. And that's what we're going to be doing with spectrophotometry. It allows you to find concentrations of solutions and analyze mixtures. So see you again, guys, with another topic in chem.